Hi, my name is Willie Honor. I am a firmware engineer for Medtronic, which is a medical device company based out of the Twin Cities area. I got my electrical engineering degree from NDSU, working as a firmware engineer now, and then I am currently working on my master's in software engineering. So this course, Empirical Methods in Software Engineering, is part of the curriculum for that. And for this presentation, my topic is focusing on analyzing metric data, which is a concept we talked about in the class, and then I'm relating it to a research paper titled Investigating the Impact of Metric Aggregation Techniques on Defect Prediction. So for this presentation, I'm going to start with talking about some of the concepts that we learned in class relating to analyzing metric data, and these concepts are also used quite a bit in this research paper. So then from there I'm going to talk about the research paper. I'll go through the introduction, the experimental design, I'll talk about the results of the research, and then the conclusion. So first, like I mentioned, I'm going to talk about some of the concepts that we learned in class related to analyzing metric data. The first I'll talk about is the different measures of central tendency, which are used to summarize the average values of the attributes or of the data set. Now these were taught a long time ago in school, probably in elementary school that we learned them, but they still come to play they're still used in research today at a much higher level. So the mean is the average values in a data set. The median is the value that divides the data set into two halves. If there's an odd number of values in the data set, the median is that middle value. If there's an even number of values in the data set, the median is the average of the two most middle values. And then the mode is the value that has the highest frequency in the distribution. For measures of dispersion, there are the range, standard deviation, variance, and quartiles that we discussed in class. And essentially the measures of dispersion are used to indicate the spread or the range of the distributions in the data set. The range is the easiest to calculate. It is the difference between the highest value and the lowest value in the distribution. The standard deviation is used to measure the average distance that a data point has from the mean. And the variance is a measure of variability. And it's related to standard deviation because it is the square of standard deviation. And then quartiles are important as well. Quartiles divide the metric data into 4 equal parts, which you can see in the diagram on the right there. Quartiles are also used to compute the interquartile range of the distribution, which is equal to the upper quartile minus the lower quartile, where essentially it's the interquartile range is the range of the lower quartile to the upper quartile. Another concept we talked about are data distributions, which essentially the shape of the distribution of the data is used to describe and understand the metrics data. And there are symmetrical and skewed distributions, and then another topic is the bell-shaped curve. So for a symmetrical distribution, one half of the data points lie to the left of the median, and the other half of the data points lie to the right. For a skewed distribution, there are either low or high data values that make the distribution imbalanced. And then a bell-shaped curve it's known as the normal curve, and it's important it's a smooth and unified curve that is perfectly symmetrical. So the diagram on the right is an example of a bell-shaped curve where, as you can see, 68.3% of the area under the curve is within one standard deviation of the mean. So that is what defines a bell-shaped curve. There's also different types of analysis that we learned in class that are important. So histogram analysis is a graphical representation that depicts the frequency of occurrence of a range of values. Now, it's typically used to analyze the normality of the data set, and the diagram there below is taken from our textbook, and it's just used to show what a typical graphical representation of histogram analysis would look like. On the right there is outlier analysis, which is the process of identifying and examining outliers. And it's used to help us to prevent distorted statistical results. And a common usage of outlier analysis is developing box plots, where essentially any data point that lies outside of the start or end of the tail would be considered an outlier. So that was a overview of some of the important topics that we've learned in our course related to analyzing metric data. So now I'll transition into talking about the research paper that I looked into. So in this research paper, it talked about how code metrics are collected at the method level, and then they're often aggregated using summation to capture system properties at higher levels, such as at the file level. Defect data is often available at these higher levels, so the aggregation allows researchers to build defect prediction models. And recent findings in research preceding this research that I'm looking at indicate that aggregation is likely to inflate the correlation between size and complexity metrics. So the researchers developed these three research questions. Number one, what are the aggregation techniques that do not inflate the correlation between lines of code and other metrics at the file level? Research question number two, do different aggregation techniques convey different information? And then the third research question, does the type of aggregation used in defect prediction models matter? So these are the three research questions that guided their research. So now I'll talk about the experimental design that the researchers used. And basically the purpose of the research was to explore the effect of aggregation techniques on the correlation between types of code metrics. So they used 9 different aggregation techniques. So summation, which has been shown in previous research. And then in addition to summation, they also looked into measures of central tendency, specifically looking at mean and median. They also looked at measures of dispersion, specifically looking at standard deviation and interquartile range. And then they also used skewness and kurtosis in terms of shape or data distributions. And then the last techniques they used were income inequality by using the Thiel index and the Gini coefficient. The code metrics that they used were lines of code, and then they used McCabe metrics as well as Halstead metrics, which I'll talk about in the next slide. And then their open source projects that they used for this analysis was Eclipse, Apache Ant, and JEdit. Eclipse is a cross-platform IDE that has many different plugins that can be used. And then Apache Ant is a build tool that is implemented in Java, and I believe that it was originally introduced to as a substitute for Make. And then JEdit is a Java-based text editor that is targeted for programmers. So the graph on the table on the right here describes the different code metrics that were used. So I mentioned lines of code, and then for the McCabe metrics, they use the metrics of cyclomatic complexity, essential complexity, and module design complexity. And essentially, these are used to estimate complexity by using the number of forks in the corresponding control flow graph. And then Halstead metrics that were used were program volume, program difficulty, length, level, intelligent content, programming effort, error estimate, and programming time. And the Halstead metrics also estimate complexity, but they estimate it by using the number of operators and operands. Now this diagram here shows the approach that the researchers used in their research. So this version archive here is essentially using the different versions that they looked at in terms of JEdit and Eclipse and Apache Ant. So they would take that and they'd perform metric collection at the method level using the method level metrics. And then from there, they would use the aggregation techniques to come up with file level metrics. And then they used that as well as post-release defect data as inputs into regression models. And then they used regression models, evaluated and analyzed the results from there. So this diagram is taken directly from the research paper, but it shows a high level of their process that they used. So with the 12 metrics and the 9 different aggregation techniques, that gave them 108 predictors. So from there, they used 2 different types of analysis, correlation analysis and multi-collinearity analysis. The correlation analysis was used to analyze correlations among the predictor variables. And then from there, the variables that were retained from that analysis were then further analyzed to check for potential multi-collinearity. And this multi-collinearity analysis considers how well each variable is predicted by the others. So essentially, with this process, highly predictable variables were discarded iteratively until all the remaining variables exhibited low levels of redundancy. And then the performance measures that were discussed in this research. So the predictor variables that I just discussed in the previous slide, those are the independent variables. And then the dependent variable is fault proneness of a software component. From there, linear and logistic regression models were built to study the impact on such metrics on the accuracy of defect prediction. The accuracy of linear models specifically were measured by computing the mean squared error. And then for logistic models, that accuracy was measured using the area under the ROC curve. So now I'll talk about the results related to their research questions. So research question number 1, I'll repeat, it was, what are the aggregation techniques that do not inflate the correlation between lines of code and other metrics at the file level? So what they found was that the increase in correlation depends on the metric considered as well as the aggregation function used. Most aggregation functions other than summation generally tend to decrease the correlation rather than increase it. So in line with previous research, they found that summation tends to increase correlation at the file level. They also found that summation results in the highest increase among all aggregation functions for most of the metrics, and mean, standard deviation, and interquartile range show similar patterns to summation, but with lower increase rates. And the overall tendency among median, measures of shape, and income inequality is used to decrease the correlation with lines of code at the file level. So for, I guess, the main points in the results that they found related to this research question could be summarized as summation increases file level correlation between most of the studied metrics and lines of code. And then number 2, second point is that median, measures of shape, and income inequality tend to decrease such correlation. For the second research question, do different aggregation techniques convey different information? They presented several different box plots in their research, and I just wanted to show an example because it's a topic that we talked about in our class. So I want to show how that related to what we're learning. And essentially this box plot here is used to analyze the distribution of the redundancy measures for each aggregation of lines of code across the 12 data sets. To summarize the results that they found, number 1, each of the studied aggregation techniques except for Gini provides a non-redundant signal for at least one code metric. And the second point is that summation exhibits non-redundancy for all metrics. So in terms of this research question, number 2, you could draw 2 main conclusions: that different aggregations convey different signals about the underlying metrics, and therefore code metrics could be represented at the file level by several non-redundancy signals, which is more informative than using only one type of aggregation. And for the third research question, does the type of aggregation used in defect prediction models matter? They found that linear models built using summation outperform the other aggregations, and similarly, logistic models built with summation generally tend to outperform the other aggregations. So very similar between the 2 different types of models, but logistic models aren't fully outperforming the other aggregations, but generally do. And then aggregations pertaining to the same family yield similar results. So, for example, different aggregations of measures of central tendency tend to yield similar results. Different, like standard deviation, interquartile range, related to measures of dispersion, tend to also yield similar results as well. And they also found that incorporating all aggregations in the same model does not enhance the accuracy of linear or logistic defect prediction models. So to summarize their results of their findings related to this research question, the studied aggregations do not have an additive effect on the accuracy of defect prediction, and regression models built with all aggregations at once are not better than those built using only summation. So, in conclusion, why was this research performed? Defect prediction is usually conducted at the file level, but many code metrics are defined at the method level. So to overcome this problem, aggregation of the metrics is performed to build file-level defect prediction models, and this research was specifically focused on investigating 9 different aggregation techniques relative to their impact on defect prediction. And what we learned as a result of this research is that different aggregation techniques do convey different statistical information, but their collective impact on defect prediction does not outperform simple summation. And we also learned that building logistic and linear defect prediction models that incorporate more types of aggregations do not have a higher predictive power than those built using only summation. So that concludes my presentation. I have a references slide here. The first reference is for our textbook that I took information and some diagrams from for this presentation. And then the second one is the research paper that I was focusing on. So with that, that concludes my presentation. I just want to say thank you for listening.